Okay, we have some odds and ends to cover, and I want to make sure we go through them. So this is a little bit of this and a little bit of that in this particular lecture. So one thing we haven't covered yet is settlement due to lowering of the water table, all right? So what I want to find is delta H at t equals infinity due to lowering of the water table. Now, what do I mean by that? Let's look at our soil profile here. So here's my t equals 0 minus, here's the t equals 0 plus to infinity. And if I look at t equals 0 minus, what do I see? I've got gravel over clay, and then I have my rock down there. The water table at t equals 0 minus is at the ground surface. And what I'm worried about is settlement of this clay due to, now I'm going to lower the water table at t equals 0 plus to t equals infinity down to the top of the clay. And what we're going to find is that is going to cause settlement. So I'm going to show you why and how you can calculate it out. Now, and we'll see why it's important. Now we're going to take our point of interest at the center of the clay layer. So that's 50, that's 90, so 70, at a depth of 70 feet. Here are our unit weights in pounds per cubic foot. So let me just write that down here. This is pounds per cubic foot. And and here's our clay properties, C epsilon R, C epsilon C, and OCR. Okay, so how do we handle this problem? Now remember, we haven't done this time rate of, well, it's not a time rate of settlement problem, but we haven't done a settlement problem in a little bit. So we have our point of interest here. It's at a depth of 70, and our times are what? 0 minus, 0 plus, and infinity. So, again, what do? At 0 minus, I look at the 0 minus figure and get my sigma v, u excess, u water table, u, sigma v prime from the t equals 0 minus figure. So if I look at here, so what do I have? I've got my gravel here, and it's completely saturated. So I'm going to use 130 for the gravel, so 50 times 130. In the clay is saturated, and now I'm going 20 from 50 to 70, so 20 times 105. That gives me my sigma v at t equals 0 minus. At t equals 0 plus, I look at the t equals 0 plus figure. At t equals infinity, I look at the same figure. So let's do our sigma v. Well, now what? Now we're going to say the water table's down here, so I'm going to say the gravel's dry. It may not be completely dry, but we're just going to use that. So we have 115. So 50 times 115, again, plus 20 times 105, I get 7850. It's the same at t equals 0 plus as it is at infinity. My u excess. Okay, so what do I have here? I've got, what do we know? We always know that at 0 minus, the u excess is 0. At infinity, the u excess is 0. So what is the u excess at here? Well, we can do it in two different ways. One way is that, what do I know? Let's look at this picture, and let's complete the t equals 0 minus values. And what do we get? Well, u excess is 0, of course, it's at t equals 0 minus. My u water table, well, it's 70 feet here. So it's 70 times 62.4. So I get my u by adding those two together. And then I get my sigma v prime, what? Sigma V minus U is my sigma V prime. Okay, so what do I know has got to be true at t equals 0 minus and t equals 0 plus? Well, these two are the same. Remember, those are always going to be the same when there's no time going past. The effective stress doesn't change. So we have those two the same. So in other words, at t equals 0 plus, I have this number. I now have this number. And what does that tell me about the U? Well, I get the U from what? I know that sigma V minus U is equal to that. So I can calculate out my U as simply the 7850 minus the 4232, and that's going to be equal to, there's a little bit of round off here, but it's going to be 3610. That's going to be that number. Once I have that number, now I know my what's my U water table? Well, my U now at t equals 0 plus, my water table has moved down, and so my water table now is what? It's going to be 20 times 62.4. And that means that this 2362 comes from the 3610 minus the 1248. So that's going to be equal to 2362. So I'm able to get my excess pore pressure there. Okay. Now, so I can fill that in. And then now I go to t equals infinity. And like we said, this is the same. The U excess is 0, goes to 0. The 1248, well, I can see the picture, right? Again, it's the same. And so that means my U is 1248. So at t equals infinity, I have 7850 minus 1248 gives me 6602. So notice, so what's happened here? I had an effective stress in my clay of 4232, and it goes up to 6602 at times t equals infinity, time t equals infinity. So my OCR is 1. So what does that mean? When I draw my plot, I'm going to have, the 4232. I'm going to have the 6602, and that means my settlement will simply be, or my strain will be simply C epsilon C log sigma prime F over sigma prime I. So my C epsilon C is given to be 0.35. I use that there. 6602, 4232, and I get my strain is 0.0676. Well, the thickness of the clay, H, is 40 feet, because this distance is 40. I put that into here. I put the 0.076 here, so 0676 here, and I get 2.7 feet. So notice what has happened here. So 2.7 feet of settlement. Now, what has happened? I've only lowered the water table in the gravel, right? I haven't done, in a sense, I have not removed water from the clay. The clay is still saturated. Clay's always been saturated. I just lowered the water in the gravel, lowered the water table in the gravel. I end up with 2.7 feet of settlement, pretty significant. Of course, part of it's the soil properties, but no matter. The lesson here is that if we lower the water table, we can get settlement and we can calculate out what that is. Now that has a lot of big implications because, when do we lower the water table? Well, it can happen a lot of different times, but certainly one time is if we are going to, for instance, if we are going to make an excavation and I need the excavation to be in the dry. So let's look at this particular situation, for instance. Here's my water table in my soil, and let's just say I have a sand layer here. What's going to happen? That sand layer is saturated. If I dig a hole here, the water is going to come in through the sand, and it's going to fill up to this level, where that's that level. And so I can't really dig that hole. I can't dig it in the dry, and the water is going to fill up our hole. So generally you don't want that. So one way to avoid it is to change the shape of the water table by pumping. So if I put in a well here and a well here and pump water out, what can I do? Now, I'm put in a series of wells because, for the length of the excavation and all around it, 3D. What I'm doing is I try to lower the water table, below this sand here, obviously, and make sure, well, I need to pump through the sand as well. I need to make sure. And you may need to cut things off here, to make sure that you can keep the water level down. So, little tricks, but no matter, your goal is to pump and to lower the water table, and get it below your excavation. Well, that's fine, but look what we've done here. I've done exactly. In a sense, if we have some clays in here or anything like that, what have I done? I've lowered the water table in this region, and maybe I have a building next door. Well, that might be bad for that building because I can create settlement below my next door neighbor's building, and can cause a lot of problems for my next door neighbor. So you got to be very careful with this. Is what I'm going to say, and it's because of this. This effect. It's not obvious until you start doing the calculation. So lowering the water table has some implications, some settlement implications you need to take into account. And, there are some claims that the Millennium Tower in San Francisco was affected by lowering of the water table, and that may be one of the reasons that it's tilting. Not concluded, but there are at least some thoughts that could be the case. So it's a big issue. And the other common location that you have this sort of problem is there are cities that use groundwater for the city water supply. And what happens? They're pumping out the groundwater and the entire city is sinking feet, like New Orleans, like the city of San Jose in California. They are sinking, and they can sink even below sea level, and it's a problem. So if you do that much pumping, it can cause a lot of problems. Okay, I want to talk about another problem, going back to our wall design, where we have our rock face, and we have, we're just putting in dry gravel or dry sand behind it, and we have to analyze this wedge. I'm just going to, tell you the geometry is a little bit more complicated now. So I have in other words, I have 65 degrees there and 40 degrees there, and I have my, intersection there, and I need to calculate. I need to draw this free body diagram of this wedge here. So remember, my goal is to here's my wedge. I have the weight of the wedge, and then I got to have a normal and a shear. Normal and a shear. And oops. And, I need to get the weight of that, which means I need to get the volume of this. The volume of that is what? The area of that triangle times the thickness. We usually take 1 meter. We're doing everything in meters, so we're going to do 1 meter perpendicular to the paper. So in other words, I need to get the area of that. Now, people struggle with this a little bit, strangely, because it takes them way back to high school geometry, which they've forgotten. And just if you remember this triangle, so I'm just going the base B, the height H. How do I get the area of that triangle? Well, it's still 1/2. So the area of that triangle is still 1/2 B times H. Okay? It doesn't have to be a right triangle. I can get the area of that triangle as 1/2 B times H. That's just basic high school geometry. So don't forget that, because what does that mean for this? This is not a right triangle. So I can use the knowledge of that to get my area. In other words, I can take this distance, that can be my H, that can be my B, and this distance here is my H. If I can get those two numbers from this geometry, then I can easily get the area of that triangle. So people sometimes struggle with, I've found that students struggle with getting these. There are different ways to get it. I could also get the area of this right triangle here, and then find this one as there's my B, and there's my H. So different ways to get it. However, whatever numbers you can come up with, you can easily get the area of this triangle, either in 1 step or 2 steps or however you need. So now in this particular, I've given you all the numbers here in a way, and so for this one, the easiest way to do it is to do as I've shown, take that triangle and add them together. So because I've given you this distance, so we'll call that B. This distance here is my H for the triangle 1. This distance here we can take as my H for triangle 2, or vice versa. So I can get, so it's 1/2 B times H. So I have, for triangle 1, 1/2 of 2.8 times 3.87. So that's this distance times this distance. And then we're taking 1 meter perpendicular. That's the volume. I have my unit weight is 18. So I get the weight of that triangle. And then I get the 1/2 2.8 times 6. For that one is the area of that. That gives me the volume. And then again the 18. So I can get the weights of both. So if you have something that looks like that, here's how you can get the weight of your wedge very easily. So okay, so once we have that established, now what we need to do, of course, is, so I have my W, that goes there, and then what? Now I just need to find my N2, F2, N1, F1, and remember that that N2 and F2 are related, N1 and F1 are related. How are they related? Well, remember it's a friction thing. The coefficient of friction times the N2, coefficient of friction times N2 gives me F2. Coefficient of friction times N1 gives me F1. So my coefficient of friction, I'm going to take as my tangent of phi prime, or tangent of delta. So in this case, I've taken my, tangent of delta, phi prime, or the delta, the 0.8, accounts for smoothness of this wall and smoothness of this rock surface. So where you're given that the delta is 0.8 phi prime, so my coefficient of friction mu is what? Tangent of delta. So tangent of 0.8 times 42 is 0.664. So my F2 is 0.664 N2 and F1 is 0.664 N1. And so I only have, my only unknowns are N2 and N1 when I do my problem. So here they are. So we have, we just calculated that. This is N2, that's 0.664 N2. This is N1, this is 0.664 N1. So now I simply take the sum of the forces in the x and y direction. I'm not going to go through all the geometry, we did that before. But remember, I always like to have the angles with respect to the x-axis. We know that that's 65 degrees. So that means what? That this angle is 65 degrees with respect to the x-axis, and then the complement of that 25 degrees for that one. So, or not the complement. So 90 minus 65 is 25. So once I have that, then I take the sum of the forces in the y direction equals 0. Well, if I do everything right, I should see sine of the angle. Sine of 25, sine of 65. I'll let you pause the video and look at how that is. We've done that enough times. And then I take the sum of the forces in the x direction. If I've done everything with my angles with respect to the x-axis, then everything's going to be cosine, because that's x, I get cosine. This is y, so I get sine. So we don't have to think about it a lot. It reduces errors. So pause it, look at that, you can do that. We have two equations, two unknowns. I solve for N1 and 2. I get N1 is 173, N2 is 108. I'm mostly interested in N2 and F2, because why? Because I know, so I find those, N2 and F2. This goes to the left, so when I analyze the wall, it goes to the right. So I have 108 to the left, I have 108 to the right. I have 71.9 going up, I have 71.9 going down. So they've got to be equal and opposite because they are adjacent free body diagrams. So when I'm analyzing the wall, here's my wall. I have those values, which is what I want. The weight of the wall is we have to compute that. So we have these dimensions for the wall, 6 times 1.5, because it's a rectangle. So the weight of the wall is going to be 6 times 1.5 times 1 perpendicular to the paper, 26 kilonewtons per cubic meter for the concrete. I get the weight of the wall is 234 kilonewtons, so I put that on there. So I have this. I'm going to do overturning, and so I'm taking moments about this point. We have nothing at the contact because we're assuming that it begins to rotate like that about point A, loses contact at the base, And I have my overturn. Remember, the combination of these two give me my overturning, because that's the force on the wall. And then my resisting is simply the weight of the wall. So we've done this enough times, so I'm not going to go through it. But we end up with resisting of 176, an overturning of 108, and we get a factor of safety of 1.625. So, okay. To analyze sliding, now what? Now, for sliding, we do have contact at the base because there's contact there, it's sliding. And what do I know? Everything's dry, so to keep everything in equilibrium, I have to take into account both of these forces here. So I have this going down, I have that going down. And so I had to take the sum of those two. So that's got to be 306 for N3. That gives me my N3 tan delta is my F3. And again, the delta is 0.8 times 42 degrees. Gives me 2 or 3 kilonewtons between the wall and the base. Yes, that's the delta between the wall and the base. So my sliding resistance is 203. My sliding force is the 108. And so I end up with 1.88 as my factor of safety against sliding. So if we look at this, what did we have? We had for overturning is 1.625. So overturning is more critical, 1.88. Okay, you can do this one. So I want you to do this one. Now notice there's a little twist here, and that is that I'm saying that this is a very rough surface. Well, I'm going to give you a hint. What does that mean? When I say very rough, that means that I can take delta equals 1 times, delta is going to be 1 times phi prime. And that's for very rough. Now here I'm saying that delta at the wall is 30 degrees. So, in other words, the delta here is 40 degrees. The delta here is 30 degrees. And then I talk about the delta down here is 20 degrees. So we have 3 different deltas. It doesn't complicate things very much, but you have to think about where you are in order to get the friction. Which delta do I use for those 3 different surfaces? So go ahead and pause the video here. The geometry is much easier. You should be able to figure that out. And get the weight of this, put the dimensions on. You got to figure that out. You have to figure that out. That's that. So, okay, so pause the video and do this problem for overturning and sliding. Okay, I assume you've paused the video and you've done it, so we need to find that value of x there. Well, what's that value of x? Is 15 tangent 30. Because this angle here, this angle here is 30 degrees. Okay, so it has nothing to do with delta. It has everything to do with the angle right there. So it's 8.66, so this distance is 8.66. And we get our volume from 1/2 the base times the height. Height is 15 feet. There's my volume. My weight, I have to multiply by the unit weight of my soil, 120. So that goes there, that goes there. And I get the weight of this. I get that weight of that wedge. Again, now you got to look at these. Along this very rough surface, well, what do I have? I've got my N1 and F1, right? So my N1 and F1, well, my phi prime is 40 degrees. Since it's a very rough surface, I put that together, and that tells me that on this surface here, I have 40 degrees. So N1 tangent of 40 for that one. Over here, I said to the wall soil is 30 degrees, so it's going to be N2 tangent 30. So I get 0.577 N2, 0.839 N1 are my F2 and F1s. So again, I'm not going to go through some of the force in the x direction, some of the force in the y direction. You can all do that. Again, I put in, so this is 60 degrees with respect to the x-axis. That's 30 degrees with respect to the x-axis. That means when I take the sum of the force in the x direction, I always have cosines. Cosine 30 to cosine 60. Take the forces in the y direction, I have sine 30, sine 60. I'm going to let you pause the video and look at how those are done. I have equation 1, equation 2. You can put that into your calculator or however and solve it. You get that N1 and N2 are these. And that means what? I'm mostly interested in F2. How do I get F2? I get F2 from this. And so I now have N2 and F2. And I now analyze the wall. Notice the wall, I can get the weight of the wall is 4 times 15 times concrete is 150 pounds per cubic foot. So my weight of the wall is 9,000 pounds. I can now put my forces on. Again, this is going to the left, that's going up. So I want to the right and down. To the right and down. And there's my weight of the wall. I'm going to assume 1/3. We don't quite know that, but we're going to take it 1/3. That's what we normally have. And then again, for my overturning, I take both of I take both of those into my overturning, and I take this one for my resisting. I get a factor of safety of 2.84. For sliding, what do I have to do? I take that plus that gives me that. Then this is going to be, now notice at the base over here, so now I'm at the base. I said use delta equals 20 here. So I'm going to use tangent of 20 degrees. So 10.35 or 10,359 times the tangent of 20 gives me the 3770. So that goes there. So I have my sliding force, my sliding resistance, the ratio of those two, 1.6. So in this case, sliding is more critical. Okay, that was another problem there. Another one, find the pile capacity at both t equals 0 plus and t equals infinity. So another problem to work. Okay, so now I have sand, I've got clay. Notice at the tip, what do I have? I've got clay. I haven't specified anything new, so I have clay at the tip. Okay, so what does that tell you? Well, it's probably going to be a friction pile. Or it's going to be a friction pile. I don't have much tip resistance. It's a square pile, 1 foot, 1.5 foot by 1.5 foot. Here are our properties. The list of properties is getting longer and longer. Water tables at the ground surface. I have 20 feet of sand and 40 feet of clay. So gamma saturated, C prime, Phi prime, SU over sigma prime I. Delta, Phi prime remolded. Alpha, K. Okay, we got all of these factors and properties that we have to use. So how does it come out? So what do? Again, we now have, we got to get the side resistance first. Well, we're going to get the side resistance first, which means what? I've got to have 0 and 20 minus for the sand, 20 plus and 60 for the clay. So those are my depths. I get my sigma V's at those depths. You could all do that. I'm not going to go through it. I get my U's at those depths, yeah, from the water table at the surface. Sigma V prime is sigma V minus U as usual. I'm going to get my sigma H prime. How do I do that? I use the K values. So the K's, someone didn't put it there. What's going on here? There's my K's. My K's are both 0.8, okay? So I kept that simple, so I should probably put those in there here. So .8, 0.8, and those are given. So what do I have? I've got, when I get my sigma H prime, that times 0.8 is that. That times 0.8 is that. That times 0.8 is that. So I got my sigma H primes. Now what I'm going to do is I'm going to make this simple. I'm going to have the tau ff at t equals 0 plus the tau ff at t equals infinity. Okay, so for the sand, it doesn't make any difference. It's going to be the same. So for the sand, it's going to be the 921.6. Now, how did I get tangent at 25.3 degrees? How did I get 25.3 degrees? Well, I'm using my delta in my sand, which is 2/3 phi prime. The phi prime is 38. So 2/3 times 38 equals, well, there it is right there, 25.3. So we have 921.6 times tangent 25.3. That's 435.6. That's my tau ff in my sand. And so I have it, here, t equals infinity, here, t equals 0 plus. It's the same in the sand because it doesn't matter whether it's t equals 0 plus or t equals infinity for the sand. But the clay, it's not the same. So for the clay, what do? Well, I need to use my SU over sigma prime I of 0.67. Here, the 0.67, my sigma prime I is 1152. 0.67 times 2656. So that gives me my SU at those depths, but then I have to apply my alpha factor of 0.9. So I put in my 0.9 there to get my tau ff. Remember the alpha is because of the the smoothness of the pile and disturbance of the clay, etc., etc. So I get a slightly reduced tau ff. So I have a tau ff there, I have a tau ff there. Then what? Now here's at t equals infinity, what's my tau ff? Well, now for my clay, what do I have to do? I have to use I have to use this failure envelope here, which gives me C prime plus sigma H prime tangent phi prime. C prime, sigma H prime tangent of phi prime, except that I can't use the phi prime. I have to use my here's this, well, okay, I have to use my 2/3 here and my 0.75 here. So I have to use both of those factors. 2/3 times 0.75 is 0.5. So that 0.5 comes down into here times my phi prime of 22 degrees. So I have to use both those factors to get my essentially phi prime, but it's, it's the factors times phi prime. So I apply this equation to both of these, and that's what I get. That's how I got both of those using that equation. So now I have my tau FFs at t equals 0 plus. I have my tau FFs at t equals infinity. I do my tip resistance. Notice the tip resistance is in clay. I have to have my t equals 0 plus tip resistance. I have to have my t equals infinity tip resistance, because that's two different things, right? Because it's the clay. What do I have? I have to get my SU at 60 feet. Why the SU at 60 feet? Because my clay tip, my tip is in the clay at 60 feet. So how do I get that? SU at 60 feet is 0.67, which is what? My SU over sigma prime I times my sigma prime, 2656. So, where'd that 2656 come from? Well, we already figured it out. It's right down there. So, take that value. That's a handy value to have. That 2656 we already figured. And we get SU is 1780. So, when I apply this equation, what happens? I put SU, as my C prime, so that's my 1780. The NC star, how do I get that? That comes from at phi prime equals 0, right? Means that NC star equals 9. So how did we get that? That goes back to the our plots. So we are chart here. So we're at 0 because it's tough, right? Total undrained fast, which means that what? We have a phi equals 0 situation. Why? Because our failure envelope for our clay looks like that. That's SU. So zero slope, which means that we have a friction angle. We use the friction angle 0, and so we're here, and we get approximately 9 there for my NC star. And notice my NQ star is 1 at that location. So we have NQ star is 1, NC star is 9 from that chart. The Q of 6400, where does that come from? Well, that also comes from our plot here, or our chart here, table. There's my 6400, that comes in handy. That's the total stress, right? Why is it total? Because total undrained fast in the clay at t equals 0 plus. So total undrained fast means I use total stresses. So that gives me my 6,400. Now here's a little hand waving here, and I'm going to apologize, but if we calculate out the pile weight, it's approximately 6,400 stress. The stress is 6,400. So due to the pile weight. So everybody, this is what they do. They just get rid of this term. So I'm sorry, this doesn't quite fit with the methodology that we've been doing, but this is what everybody does, and it's approximate. It works good enough. So we just get rid of that term. So basically, we just end up with a C and C star term, and that means we have 16,000 PSF. At T equals infinity, same equation, but now what do we have to do? Well, now we have to use our phi prime equals 22 degrees. Where does that come from? That comes from remember we're down here in the clay, so I have to use my phi prime in the clay. I don't apply any of these factors here. I don't apply the factors to the down below there. Why? Because, we haven't done all this remolding of the clay. So and we're not relying on shear. See, this delta is for shear, right? This is tip. We're talking about the tip resistance down here. That's what we're talking about, the tip, not shear. So we are going to use 22 degrees now in our chart. 22 degrees takes us to over here, and that's what's approximately 18 or something, and that one's about 40. So approximately, I don't know what I use, but approximately 18 and 40, and okay, 15 and 36, close enough. So and then what? Now I actually use my C prime. I actually use the C prime, the real C prime for T equals infinity. So, that's 400 is my real C prime. It actually goes into this, so there's my 400. And we just got that. We just got that. And what is my Q? Again, the 2656 is what? Now we're eds. So effective. We now want the effective stress there at that Q. And so we've already calculated it. There it is. Multiply that out, and I get my Q tip of 54,240. I'm not going to go through all of this, but you can get all these. I now plot these values up. So in other words, I'm plotting these, and I'm plotting these. T equals 0 plus, T equals infinity. When I get these, I'm going to get the volume of 1, 2, and then 3 at the tip. Okay? So the tip, the 16,000 came from where? 16,000 came from here. And the 54,240 came from here. And so I'm getting all the volumes there. I get all the volumes there. You can pause the video to look how to get those. And remember, I end up with 4 sides, okay? So I have these, the four of those things. So for the 1 and 2, 1 and 2 have the 4. So there's a 4 there. 3 does not have 4. It doesn't multiply by 4 because there aren't 4 of those guys. There's one at the bottom. I got 4 at the top. 4 of the shears. So that's the only trick that you have to realize. You add them all up. There's my T equals 0 plus. 337 kips. And then my T equals infinity. I end up with 15 kips. So they're pretty close, but this one is more critical. So you have to design for the more critical, the t equals infinity. So that can happen sometimes. So most critical, that 315, that's what you have to design for. Okay, I'm going to stop there.